microscopy, which I guess most of you know. When you have a conductive surface, you come with a conductive tip, scan it along, and measure the tunnel current which flows between your tip and the surface, which can give nice images like this here. This is an example for indium arsenide. You're also sensitive to chemical information with this. But the method has usually been, or has initially been developed for flat and clean surfaces. And we have something like the opposite structure here. If we have nanowires that have such a large aspect ratio, so how can we do STM on these things? Well, we could even do it on top, but that's not a topic for today. So what we usually do is that we break off these nice structures, that we put them onto a suitable substrate. This is an overview image here. Here's a zoom in AFM image where we have a single nanowire, in this case made of gallium nitride, so that we then can come along with our STM tip and position it here on a side facet of such a nanowire and scan the surface here. The next challenge is that these 3,5 materials, when they have been grown and are transported through air, that they oxidize. So we need to get rid of the native oxide on these surfaces, and that we do by annealing them in atomic hydrogen. And if that works well, we can resolve their structure, even zoom further in and see atoms on the side facets of individual of the structure. So if we here have the entire wire, what we are doing now is that we zoom in and go here on the side of one such facet here, and then we will see structures like this here, where we can see in this case, group 5 atoms here of gallium arsenide, indium arsenide, and phosphide, and you see the structures, different type of nanowire surfaces. The cleaning, of course, is a bit of a challenge. You can see here for indium phosphide, for example, we have some patches of native oxide left. For other materials, it works better. So after this motivation for why we want to use scanning tunneling microscopy, STM, and other surface techniques on these nanostructures, let me introduce the outline of this talk. So I will, after introducing this, I will focus on different heterostructures. So that is not only the nanowire surface by itself, but especially what's interesting is what happens if we have an interface towards, in this case here, another crystal structure. That is a special thing for these 3,5 nanowires, that they can have different crystal structures within one nanostructure. Beyond this, the surface topography will also look at surface electronics through spectroscopy. And we even show some examples that we can modify our surface. And then also we have used different type of interfaces like doping interfaces. And in the end, I will go towards device structures where we use STM even during operation of the devices. So getting started here, again, this is the surface of a nanowire, indium arsenide nanowire in this case. So what we can see directly from the STM images is something like the surface topography and also the crystalline quality. As in this example here, okay, you see nice areas where we can see these individual dots here, which are the atoms, arsenic atoms in this case. But you can also see the large number of lines here, which are defects. There can be stacking faults, that the crystal ordering is changed, or other type of defects. But what we also see is that this layer is entirely flat, in a large flat terrace, and that we have some islands here on top. And then if you have a very patient student who is sitting in the lab and doing image for image for image, you can end up with a picture like this. This is 36 individual STM images stitched together here to follow more than 3 micrometer of an entire nanowire with atomic resolution. And the interesting feature here was that we found exactly one monolayer high surface depth. So that was an absolutely straight nanowire in this case. But as I said, it becomes more interesting if we look at interfaces. And what is peculiar for these 3,5 nanostructures is that they can be engineered in such a way that you have different crystal phase in the same nanowire. This is an SEM image here, where you start after growth with the this is the catalytic growth particle. You start with the cubic structure, zincblende. Then you can switch by changing the growth parameters. You can switch to a hexagonal Wurtzite structure, and then again it's cubic, it's hexagonal, and so on. These hexagonal structures are not even allowed, or not even possible in bulk 3,5 semiconductors. So the surface structure was unknown. So it's only on these nanowires that we can resolve it. For example, here these Wurtzite 1,0 - 1,0 surface facet, or this 1,1 - 2,0 surface, which are different directions. And the zinc-blende, the cubic structure, is more well known also from bulk materials, from substrates. If we then go towards a realistic surface here, this is the same area, only in 3D or in 2D visualization. This is an indium arsenide nanowire, where this here is the side facet, which is upright, where we can place our STM tip on top. So we come here with an hexagonal structure. You see here these zigzag lines that are individual atoms, which you can follow here, atom on atom. Then we come to an interface here where the structure changes from hexagonal wurtzite to cubic zincblende. We have a different pattern here of the atoms and the surface, and it goes back to the hexagonal case here. We also see some contamination here on the surface, and then we can go here across an edge. So this is a 30-degree angle towards a different facet at the side of this nanowire. And as I said before, in addition to the structure, which is maybe nice to see how the atoms are aligned, but if you want to use such a nanowire in an electronic device, you're interested in the electronic properties that you have here. So what we can also do then is that we perform scanning tunneling spectroscopy, where we can map or we can image the local density of states. And the advantage of doing it on such a structure like this is that we can position our tip at the different places here at the hexagonal structure, at the cubic structure, and back at the hexagonal structure. And so we can be sure, without changing our STM tip, which can give different electronic properties as well. So staying in the same conditions on the same surface, just by moving across the interfaces, we can compare the electronic footprint of the different structures. And this is how that looks. This is raw data here, where we measure the differential conductivity, so the derivative of the current. Why do we that? Because this is, which is shown theoretically, this is can be considered as the local density of state at the position of the tip. So what we get here, in this case, it was a gallium arsenide nanowire. What we see, if we start with a negative sample bias here, so we are tunneling with electrons out of the sample, filled states of the sample into the tip. So we are monitoring here, imaging the valence band until the valence band states vanish because we're reaching the band gap. Then we have no states here within the band gap. We see even some dopant contributions here. And then when we go towards positive bias, so now we are tunneling electrons from the tip into the empty states of the sample. So we are probing the density of states of the conduction band. And in STM, or scanning tunneling spectroscopy experiments, the Fermi level always is positioned at exactly at 0 bias. So if we then compare these two spectra here, one taken from the wurtzite hexagonal structure, one taken from the zinc-blende cubic structure, you see directly by comparing them that there's a shift between the two spectra. So there's a band alignment between the two structures. And if we reveal that, analyze that properly, we see here that there is a conduction band offset between the two. It's the same material, only different crystal structure, only different stacking of the atoms. Still, we have a barrier here between the conduction band of both structures, both phases, of more than 200 millielectron volts. So that is a strong barrier if we want to have electron conduction through this nanowire. And this is called the type 2 heterostructure, since it's like a staggered, so both the conduction band level minimum and the valence band maximum are shifted in the same direction. Then the question came to us, since the structural transition can be very sharp, it can be at the atomic level, how well can we resolve the electronic shift, the transition between the wurtzite and zinc-blende also electronically, or how well is it defined, even if you have very small structural changes? So we went to, in this case, we went to low temperature measurements so that we have a better stability. This was done in the Brookhaven National Lab in US. This is an indium arsenide nanowire. Again, these lines that you see here, these are atomic chains, arsenic atoms that we see here on this indium arsenide nanowire. This is one facet here where we have two terraces of different height. Then we have the edge, and we have the other facet going down 30 degrees. This is a hexagonal structure, but if you